G'day everyone, and welcome back to my channel. As you can see, the Xena diode and the 4148 and the 546 transistor and its compensation capacitor, which is a 10 nanofarad, are all out of circuit. The wires from the reference board and the output that went back to it all out of circuit. And if we have a look over here, this board is as bare as it's ever been. It's literally got a couple of transistors for the Darlington output and a 47k resistor coming in to a 1k going to a base with a wire coming off the center point there. What I've done also is I've added these two little bits of board to the output. This switch here is what goes in between the 2-wire and 4-wire sense and has the 10 ohm resistors across it. So the output of that switch is the sense, positive, sense, negative. So I've put a couple of bits of board there because there's too many connections to just keep blobbing up on top of each other, especially now that I might be changing things around. Well, I've already had to change a few things around, so that's why I've done that. It'll just make it easier. And I brought over positive and negative sense and the supply current that goes to the base, so that this is the wire that normally goes to the collector of the comparator transistor, and that transistor pulls down this voltage to turn the series passed element off, or anywhere from the linear region to off, but you know what I mean. Alright, so I'm going to start designing this with basically a differential pair. Now, I figured if I use a differential pair, the reference current can flow into one side of the differential pair and go to ground, and the other side can be looking at the output voltage. That way, when I say turn the differential pair hard on, which turns the output off, I will have no voltage and current going to the output terminals from the reference board. To cut a long story short, I don't think I still got the paper here. I think I explained it well enough in the last video anyway, so I think everyone understands what I'm trying to get at here. But I know I did a really crappy drawing of a differential pair. I didn't put the collector resistors or emitter resistors if you're using it and all that sort of stuff. I was just trying to get the point across. So I'm going to use two transistors and feed the sense in one side and the reference in the other. It'll still be the emitters will still be referenced to the negative terminal, because otherwise I'd lose my negative side sensing. But the point is that the reference current will be flowing in between the reference board and the negative terminal in a loop. Well, it'll be going, the positive of the reference will be going from the base junction to the emitter, which will go to the negative terminal, and the other terminal of the reference would be, I haven't even thought this through yet, to be honest. It's a bit silly trying to explain this. Probably reference to negative. The point is, I'll be able to make it so that I don't have reference current flowing into the output. I only have what comes from the series pass element going into the output. So that's what we're going to work on here with this little breadboard. Probably have to run over a couple more wires still. I'm just setting it all up now. I don't work with breadboard too much, as I said in the last video. When it comes to precision stuff, it's just impossible. I literally got a brand new piece of breadboard here, just restripped all these wires so they're nice and clean, soldered them at the other end. You know, like, you got to keep your connections tight when you're doing this sort of stuff. Anyway, I'm going to go have a tinker around now. I'm going to grab a couple of BC546 or similar transistors just to experiment with. Maybe something else, because I think they're going out of production. I can't remember. I think they are. I think there's only like 1 or 2 sources that still make them. So I'll try and hold on to most of them from things that I specifically want them for. But yeah, I'll go grab a couple of NPN transistors of similar variety and start mocking this up and see how I can get it to perform. Now the breadboard may end up growing because, you know, like I might end up needing to put a current source in there, and the differential pair might end up needing more gain, so I might need to make a super transistor out of the transistor on each side. For those that are wondering what a super transistor is, I think the best way to explain it would just be to show you the circuit diagram of a few op amps. If you look at the input stage, you'll see 2 transistors that are sort of arranged back to back, not like a Zikli pair, however you pronounce it, but it's kind of hard to explain. I'll show you guys later, so those that are learning get to learn something new. For the rest of you already know what I'm talking about, I guess. So yeah, because that might happen and I might need to put a current source. I can't see, actually, I won't need to make a super transistor. When it comes to sensing the current shunt, that's when I'll probably need to build a super transistor, but for this I'll have more than enough voltage and current, so I won't need to do it. But I'll still show everyone what one is, just because, you know, some people out there are trying to learn. But the board could still grow. I might need to add current sources, current mirrors, all sorts of funny stuff to it to get it to behave how I want it. I'm trying to keep the entire approach of this as simple as possible. The whole idea, I set myself, just so everyone understands, I set myself a goal with this power supply build. I could easily build it in a day out of op amps and some just standard components, you know. I wanted to make it all transistor based. I was tossing it up originally. I was either going to go all op amp for the constant voltage and the constant current circuitry, or all transistor for both. I ended up going all transistor. That's why it's the way it is right now, a half mess, and everything that's in there is transistor based, and the breadboards I was mocking up constant current circuitry on haven't grown for literally a year because I've kind of canned that project. But anyway, I think I should just start getting to work because I get carried away talking. But the whole thing is, I set myself out a goal to, how do I say this? Make it all out of discrete parts, so it gives me the fun of designing all the circuits. I guess you could say I'm cheating using an LM324 on the tap changer board, but it would just take too many transistors to implement that. Like I'm using the entire 324. I'm using one stage as a buffer and 3 stages as a window comparator. So it'd be a bit tricky to do it without transistors. It would take a lot of space, a lot more transistors. So yeah, but anyway, the rest of it I want it to be transistor. If I have to throw an op amp or 2 in there for something, I might, but I'm trying to keep the guts of it transistor based, or at least you know, like in terms of other things like references, still completely analog, so to speak. No digital stuff going in there. Like, you know, the voltage reference is an ATL431B. The constant current reference is a what are they called? 51 ACN. I forget the starting letters of the component. It's not written on it by this company, but it's a reference I see. Anyway, geez, I get carried away. I'm gonna set this up, get a couple of transistors, a few different resistors, and start experimenting, and I'll come back soon. Okay, so after playing around with 5, possibly 6 transistors plus the driver comparator transistor that's back in there, and also having problems with breadboard. So that's why the wires are all soldered, because I ended up starting to use perf board. Not perf board, what do you call it? Prototype board. I've decided to screw that. Bear with me here. I know this is a little bit confusing. The way, if you can just ignore this transistor and this transistor. Oh, you know what? I should have drawn two of these. One moment. Alright, I hope this makes sense. This is, emitting compensation capacitors and diodes for protection and Darlington's stages and stuff like that. And the reference, by the way, runs off a floating supply. Right, the regulator here, that runs off the transformer. The positive here comes from the positive of the capacitor bank, the negative comes from the negative of the capacitor bank. The regulator, it's powered from the transformer winding, but it's referenced to the negative. It's important to remember that. This will be very important in a minute. Now at the moment, this is how my circuit works. You adjust the reference voltage, which is hooked up like this to this transistor, which is its emitter goes to the negative output, and the reference goes to the positive. This is how I've got sensing on both terminals. Now, with just one transistor as a comparator. So if you tie this back to here, the circuit will still work, but you lose heaps of regulation because you won't be sensing the voltage drop across this wire here. Now, my problem is this. If I stick another transistor here and try and turn it on to limit the constant current, there is still power flowing out the reference, out the positive terminal, and through the base junction and out there, right? Is it through the base junction? Yeah, it's through the base junction, right? Now, that's not good for a couple of reasons, but the problem that it's causing is that I can't limit the current to 1 milliamp, because this is supplying current to the output. So even when you turn this second transistor on hard, pulling the voltage that's turning this on down, right, there's still this other voltage. So I said, well, okay, I need that transistor added there. What if I break this here, right? And sorry about the crude drawing. Add another transistor there, right? So there's now a break here. Now, I've got this regulated supply. I can take, before the bias resistor for this, I could take some power off of there, right? Another bias resistor, and bias this transistor so it's just always on, right? So that works fine, because this transistor's emitter goes into this one's base, which goes to ground, so, and the regulator's reference to ground, you see, so I can bias this transistor on all the time. So just apply enough current to its base to make sure it's hard on, like basically in saturation, so it doesn't affect regulation. Then here's where the trick comes in. I then take another transistor, back to the actual ground point, at the end of the circuit, not the output. And when I turn that transistor on, it's going to pull this down, opening this transistor up. Now, I'm going to need, hold on, let me just think this through for a second. This transistor, yeah, so, and this works out because this transistor, it's 1 VBE drop away from ground. This transistor is also going to be 1 drop from ground. So there's going to be a little bit of a difference with the voltage drop as the load increases on this stretch of wire here through the chassis from the cap bank to the output. I'm going to have to work out something to deal with that. But basically, if I can turn these two transistors on at the same time, that point can become my constant current point, if that makes sense, for the constant current circuitry, to be able to effectively limit what comes out the output. Now, I know this might sound like a long stretch and like it's not going to work and this and that. I'll make it work. The only other way I can think about doing it is setting up a huge bias network on a long tail pair with a current mirror at the top of it, or maybe using a current mirror at the bottom and then setting up a bias network on that. But then I can't imagine how to get 4-wire, like 2-wire sensing, like sense both the rails. I hope this all makes sense. I'm sorry if it's a bit confusing. Sorry if my drawings don't make sense, but that's what I'm going to go and do now. I'm going to go and make up this circuit and see what happens when, well, see how I can interact these two bases together, and when I turn them on, will that bring my output current down to an actual 0? If it does, then that's going to be my point for the constant current circuitry to control the constant voltage circuitry. I'm going to leave it at that for this video because I don't want to confuse people here, and also it's 2 o'clock in the morning and I've got to go to bed. But I've done a lot of playing around the last day, and I've come to the conclusion that I'm going to end up using so many transistors, it's going to take up so much room. So I'm going to try and make this work, and if I can't get this to work, I'll just make it op amp based, because I've already got a constant current circuit that I mocked up out of op amps, including the leakage sense circuit as well that I was talking about earlier. So it doesn't really phase me which way I end up doing it, all transistor or op amp. Yeah, so I'm going to go and make this up now, well, not now, in the morning, and I'll make a video and show you guys how it went, and we'll move on from there. Alright, well, thanks for watching. I hope that makes sense to everybody, and I'll see you in the next one. Oh yeah, and if you like my content, please like and subscribe. I'm trying to build the channel up. Thank you. See you in the next one. Just one more thing to clarify any confusion. When I was saying about the reference voltage going through the base junction, the reason the transistor's not getting reverse base emitter junction breakdown is because there's this 14148 diode and Zener across it. That's what that's there for. That's to stop the reverse voltage from breaking it down. Just in case anyone was wondering. And the capacitor is the compensation capacitor for it. But yeah, that's how that's working. Hey, just one more thing, because I've just realized that I actually forgot to show you guys something. So just quickly, I said before something about this thing called a super transistor and that it's in some op-amp circuits. So at the start, at the input of the op-amp, this is a very, very crude long tail pair. I could draw the whole thing. I mean, it's just going to take more time. We'll just do a really simple one, just with resistors and no current source, current mirror. Just the actual long tail pair itself. I always draw things back to front. Sorry. Yeah, that looks kind of funny now. Sorry about that. I can't even look at that. Sorry, I want this to make sense to everybody. That includes people that are trying to learn, so be a little bit more neat. Alright, very crude long tail pair, right? It's not even really a long tail pair, it's just a differential pair. There's no current mirror at the bottom. But anyway, very crude differential pair. Now, in some op-amps the input stages, they take another transistor. Now, you're going to have to excuse me because I might get the orientation of this wrong, but I'm pretty sure it's something like I should have just got a data sheet up and looked at this. There's two transistors connected back to back in a really odd fashion. Like, it's something like the base goes to the collector and the emitter goes to the collector, and that becomes your new base or something like that. I honestly forget which way around it's connected, but if you go and have a look at some data sheets for op-amps, you'll see what I'm saying. It's in a lot of op-amps. Sorry, it's 2 o'clock in the morning. I really can't think. I promise in the next video I'll find a data sheet of an op-amp that has this in it, and I'll show you what it looks like, just so you know what I'm talking about. But the reason this is going to come into play is because if I end up getting this to the circuit I'm working on to work all transistor based, then my constant current circuitry is going to be transistor based too. And I can tell you now it's going to end up being at least a differential pair with a current mirror at the top and a current source at the bottom, and a super transistor on each side of the differential pair to get enough gain to sense across the current shunt. So that's why I wanted to explain what it is. Anyway, I'm going to go to bed now. I'm sure I've drawn that around the wrong way. My apologies if I did. Like I said, in the next video, I'll look at a data sheet of an op-amp that's got it in it, and I'll show you exactly which way it's connected. It's probably the other way around. Like, I wouldn't be surprised, honestly, if it's like the emitter goes to the base of that transistor and the collector connects to there. That becomes your new base, you know? Like, I just can't remember how they've done it, how it's done, but it's called a super transistor. You can look it up. Like I said, it's in a lot of op amps in the front stage of it, front end input. But yeah, I promised I'd try and explain it, and I didn't load up a data sheet, so there's at least that. Like I said, in the next video I'll show you exactly what it looks like. Alright, thanks for watching, everybody. I'll see you in the next one.